Classifying acids and bases. We're going to talk about two of them in this section, the Arrhenius concept and the Bronsted-Lowry model. In 1884, Swedish scientist Svante Arrhenius was doing experimental work with electrolytes. These are substances, can be liquids or solids, that can dissociate into ions when you dissolve them in water. He was the first person, to understand the essential nature of acids and bases. He postulated that acids produce hydrogen ions, H+ ions, in aqueous solutions. So what is that? That's basically a proton, right? Arrhenius further postulated that bases produce OH- ions, hydroxide ions, in an aqueous solution. So here's his definition. An acid contains a hydrogen atom and dissolves in water to form a hydrogen ion, H+. So here's an acid, dissolves to form a hydrogen ion, and then chlorine ion, chlorine minus. Hydrogen chloride gas dissolves in water because it forms ions and is an electrolyte. And remember, H+ is a cation because it's positive, and Cl- is an anion because it's negative. A base contains hydroxide groups and dissolves in water to form hydroxide ions, OH-. So you have a base over here, sodium hydroxide, a solid, dissolves in water to form sodium ions and hydroxide ions. Solid sodium hydroxide dissolves in water because it forms ions and it's also an electrolyte. Remember, sodium plus is a cation, OH- is an anion. In 1884, when Arrhenius proposed his definition of acids, it was a major breakthrough in chemistry. However, as it is for a lot of breakthroughs, it's not always totally correct, and sometimes it's limited. It has to be modified as we learn more about the science. For example, the H+ ion does not exist in water. Instead, it reacts with a water molecule to form the hydronium ion, right here, this H3O+. So here's the H+ ion, reacts with water, and we have hydronium. The hydronium ion is the actual species present in the solution. It is also a limiting definition for bases because it only allows for one kind of base, the hydroxide ion, such as when a metal hydroxide, like sodium hydroxide, dissolves in water. Okay, so Arrhenius can handle that, that's just fine. However, other compounds can increase the concentration of hydroxide ions in solution. So a few decades later, in 1923, two scientists, Bronsted and Lowry, and probably shouldn't put them together because they worked independently, they suggested a more general definition of an acid. This definition is more widely used. Their definition stated that an acid was a proton donor. So here's an example of that. We have hydrofluoric acid over here. It acts as an acid and it donates its H+ ion, which is a proton, right, to a water molecule, which will increase the hydronium concentration in solution. Bronsted and Lowry, again independently, then proposed a more general definition of a base. They stated that a base is a proton acceptor. An acid donates a proton, so a base accepts one. So here's an example. We have an ammonia molecule, and it will take an H+ ion from the water, and another name for an H+ ion is proton. So it's acting as a base, and there is a resulting increase in hydroxide concentration. So we can see why this is a less limiting definition, because now ammonia is properly classified as a base, even though ammonia doesn't have the OH inside of it, but it is a base, and this definition fits better. Let's put it all on one page. Acids are defined as proton donors, and here's an example. HCl giving up a proton, forming the H3O+ aqueous, and chlorine aqueous here. So HCl loses a proton. Bases are defined as H+ ion or proton acceptors. So we have the cyanide ion here picking up an H+ or a proton, forming hydrogen cyanide. So this is going to be a base. Your cyanide ion is a base. A Bronsted-Lowry acid must contain a hydrogen atom. Acids are abbreviated as H, which is the hydrogen atom, and A, which are other elements. So for example, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid. Sulfuric acid, you can have more than one H. So you have two H's there. Acetic acid. So the acetic hydrogens are shown in red. Acids, as we saw on the previous slide, can have different numbers of acidic protons. A monoprotic acid has one acidic proton, like hydrochloric acid. Di would have two, sulfuric acid. Tri has three protons, acidic protons, and that's phosphoric acid. A Bronsted-Lowry acid can be neutral, or it can carry a net positive or a net negative charge. So here, hydrochloric acid, neutral, positive, the hydronium ion, and negative, sulfuric acid. A Bronsted-Lowry base is a proton acceptor, and so it must be able to form a bond with the proton, so it can accept it. The base must have a lone pair of electrons, which we're going to label like this, B with a colon, that can be used to form a new bond to the proton. Below, you can see that the nitrogen atom of ammonia, and it's right over here, has a lone pair, nitrogen, with two electrons. Water, and here's your water over here, will act like an acid. It will donate its H+, this guy over here, to become OH-, which is this, and then the hydrogen goes over to here, and it forms the ammonium ion, NH4+. Here are some common Bronsted-Lowry bases. Now note, which of these would not have been bases under the Arrhenius definition? These two guys here, right? They don't have a separate OH-. Here's Arrhenius, this is good. The OH- group in metal salts makes these bases. Sodium hydroxide, potassium hydroxide, magnesium hydroxide, calcium hydroxide. What makes these guys bases are their lone pairs. You can see there's the lone pair with the nitrogen for ammonia, and here's two lone pairs for water. So these are bases because of Bronsted-Lowry. You may already have learned that acids react with bases. Here's some examples. Here we have HCl reacting with sodium hydroxide. The HCl donates a proton, and the OH group very nicely accepts one, forming salt and water. Over on the next one, we have HCl once again donating a proton. This time water accepts the proton, and we have the chlorine minus and the hydronium ion. Reactions between acids and bases can proceed all the way from reactants to products. For example, we have HCl plus water disassociating completely into your chlorine ions and your hydronium ions all the way, so we have a single arrow. They can also be reversible. That is, substantial amounts of reactants and products may coexist. And if we will represent that with a set of double arrows. We'll return to this later when we discuss acid and base strength. Conjugate acids and bases. Let's do a little etymology first, or entomology, not sure. The term conjugate comes from the Latin word conjugare, meaning to join together. Reactions between acids and bases always yield their conjugate bases and conjugate acids respectively. So here we have our HNO2, which is nitrous acid. It's reacting with water. It donates a proton, and it forms its conjugate base, NO2- nitrite. This base over here, water, accepts a proton, or an H+ ion, and it forms its conjugate acid, the hydronium ion. The product formed by the loss of a proton from an acid is called its conjugate base. So over here we have the nitrous acid. It donated a proton over to this guy, so it lost one, and it became this over here, the NO2- the nitrite ion. So this is the acid, this is its conjugate base. How about this guy? This base picked up a proton, and it became an acid, the hydronium ion. So this is the base, this is its conjugate acid. One more look at this. We have nitrous acid and nitrite are a conjugate acid-base pair, and water and the hydronium ion are a conjugate base-acid pair. Note, the net charges on both sides of the equation are the same. That's due to the conservation of charge, right? Because here you're neutral, and here you have -1, +1, that's also neutral. When a species accepts a proton, right, the positive charge there, it gains a positive charge. If a species donates a proton, it gains a negative charge. If a substance can act both as an acid and a base, it is called amphoteric. For example, water can act as a base or an acid depending on the situation. So for this first reaction, you have HCl plus water. Water accepts a proton and becomes the hydronium ion. So if it accepts a proton, it's a base. Over here, the second reaction, we have ammonia plus water yielding the ammonium ion plus hydroxide. It's donating a proton, so it's an acid. In general, an amphoteric compound contains both a hydrogen atom and an atom with a lone pair of electrons, so it can act like first an acid and then a base. When we examine the products and reactants of a reaction, we can identify if a substance is behaving either as an acid or a base. For example, let's take this guy over here. We have the hydrogen sulfate ion mixing with cyanide, giving us the sulfate ion and hydrogen cyanide. In this case, the HSO4 donated a hydrogen plus, a proton, to become SO4 2-. So, this species acts like an acid. It's a hydrogen donor. The cyanide accepted a proton to become hydrogen cyanide. So the cyanide ion acted as a base. Identify which reactant behaves as an acid, and remember the reactants are over here, and which behaves as a base in the following reaction. So we have water plus a methylamine ion forms methylamine and a hydronium ion. Let's see if we can do this before we pull the answer tab. You take a shot at it first so I won't say anything. Okay, I'm going to say something. The water here, how does it turn into hydronium? It picks up an H+, right? So it's a proton acceptor, so what does that make it? Pretty sure that makes it a base. And then what's going on here with the methylamine? What's the difference? It's donating a hydrogen, right? You had 3 here and only 2 here. So this should be an acid. So let's see if the answer bears that out. Water is a base. Yep, got that. And methylamine is an acid. Excellent. Some acid-base reactions are reversible, and we'll go down here. We'll talk about them later. So we can also identify acids and bases for the products. For example, we have fluoride ion plus water yields hydrogen fluoride plus hydroxide. Note that the hydrogen fluoride, one of the products, donates an H+ ion, so that is an acid. So this guy right here is an acid. The hydroxide ion accepts a hydrogen plus or a proton to become water, so it is a base. So this also works for the products when you have a reversible reaction.